Welcome to this explainer. Today, we're diving into a genuinely brilliant and, honestly, super practical piece of research from Microsoft. It tackles one of the absolute most annoying problems in modern software engineering, which is the persistent amnesia of large language model coding agents. Basically, this paper introduces a closed-loop framework that gives these agents a permanent, self-improving memory. And the best part? It does this without you having to change a single line of their underlying model.
We've all been there, right? That absolute Groundhog Day frustration. You're working with this highly capable AI coding assistant, and it makes a silly architectural mistake. Maybe it leaks a database connection, or it completely botches your dependency injection setup. So you fix it, but then it wakes up tomorrow and makes the exact same error all over again. Because it has absolutely no mechanism to retain that specific behavioral correction, it just reproduces the exact same failure mode in your next session. It's incredibly repetitive, and frankly, it just drains the productivity these tools are actually supposed to provide us.
All right, let's start with part one, the AI amnesia problem.
So let's explore why current AI assistants lack this organizational memory and how that bottlenecks our engineering. Up until now, fixing this amnesia usually meant you had to choose between three pretty terrible options. First, you could do organization-specific model fine-tuning, but that requires massive compute costs, continuous dataset curation, and honestly, it gets outdated the exact minute your team changes a coding standard. Second, you could try Retrieval Augmented Generation, or RAG. Now, RAG is fantastic for pulling in facts, like API documentation, but it fundamentally struggles with negative constraints. It's really hard to use RAG to tell an AI what not to do. Or third, you could rely on static prompt engineering, which just leads to massive prompt bloat and doesn't evolve naturally. But this research, it illustrates a much simpler, highly pragmatic fourth path. Using cheap, plain text, model-agnostic behavioral rules, it creates a really robust feedback loop without needing any model retraining whatsoever.
Moving right along to Section 2, the closed-loop framework.
Enter the closed-loop framework. Think of this as a permanent, shared diary for your AI agents, allowing them to actually learn your team's unique engineering culture. The core philosophy here is beautifully simple, summed up right in the paper. Every accepted review comment is a self-review rule. Literally, if a human engineer catches something the agent missed, it gets codified so the agent catches it next time. The ultimate and, highly ambitious goal here is to reach 0 avoidable review comments.
Okay, so how does this actually play out in the trenches? Imagine a continuous cycle, kind of like a day in the life of a pull request. First, the agent takes a stab at generating some code. But before it even presents that code to you, it pauses. It executes its own custom self-review checklist against the work it just did. Then, when you, the human, finally review the submission, you'll inevitably catch some nuanced edge case. Instead of just fixing that code in isolation, your feedback, assuming it's a generalizable mistake, gets codified into a permanent rule. And here is where the magic happens. That newly minted rule is instantly loaded into the instruction file for every single subsequent coding session. You've permanently altered the agent's future behavior.
Which brings us to Section 3, Anatomy of an Instruction File.
You might be wondering, what does this organizational memory actually look like under the hood? Well, it turns out it's wonderfully uncomplicated. The brilliant part is that it avoids complex vector databases entirely. It's really just a version-controlled Markdown file, something like AGENTS.md. Because it's Markdown, it's lightweight, human-readable, and tracks perfectly in Git. It just gets appended over time with 5 key sections. You've got behavioral rules for high-level guardrails, code standards derived straight from review feedback, a self-review checklist the agent actively runs, anti-patterns that strictly prohibit specific bad code implementations, and workflow rules, which tell the agent when to invoke external tools. It's basically a living artifact that quietly accumulates all of your team's hard-won engineering judgment.
Let's consider how a real rule schema operates in a live deployment. This isn't just unstructured, chatty text. Take Rule R17, for example. It tracks the exact origin of a severe security constraint. Server-side request forgery, or SSRF, is notoriously tricky for large language models to catch on their own. In this specific case, a human PR reviewer caught a missing SSRF policy allow list entry. Under this schema, the rule maps directly to a checklist item. As a result, the AI now automatically checks SSRF policies before submitting any new client registrations. The context is perfectly preserved and mechanically enforced.
Another concrete example from the paper really hammers this home. Any .NET developers out there? You definitely know the pain of hot client socket exhaustion. While the researchers noticed an AI agent incorrectly disposing of a factory-created HTTP client using a standard using block, a human reviewer flagged it. Under this closed-loop framework, that single comment was converted into a permanent rule. And guess what? From that day forward, the AI completely stopped incorrectly disposing of factory-created HTTP clients. It permanently fixed a highly common, super annoying resource management bug. The one-off point correction successfully became a persistent class-level constraint.
Let's jump into Section 4, the ratchet effect results.
Let's see how this builds a ratchet effect in the real world. Because Microsoft didn't just test this in some isolated lab. They deployed it across a platform of over 35 massive microservices in production. And here is the mic drop number, 0. Across 9 specific tracked error classes and 74 post-rule exposures, researchers observed exactly 0 error recurrences for ruled against patterns. Think about that for a second. Once a rule was injected into the system, the AI completely stopped making those specific mistakes for the entire observation period. The ratchet effect is absolutely real. The baseline of what the agent gets right just continuously goes up. And the knock-on effect here is just brilliant. Because the AI stops fumbling basic syntax and resource errors, human review comments massively shifted. Humans are finally freed up to do what humans actually do best. Consider the breakdown. 66% of human review comments shifted entirely to high-level architecture, API design, and performance validation. Only 14% were left dealing with low-level mechanical correctness and style, while 20% fell into other categories. The cognitive load on reviewers completely flipped from frustrating syntax checking to actual meaningful software engineering.
Finally, Section 5, elevating the human reviewer.
This fundamentally changes the relationship between the human engineer and the AI coding assistant. Instead of playing syntax whack-a-mole all day, human reviewers are basically elevated to architects. But there are 2 other incredible benefits here beyond just the code itself. First, the rules transfer seamlessly across different interfaces. A rule you add through a visual IDE agent immediately benefits a command line terminal agent because, well, they're both just reading the exact same underlying Markdown file. Second, and honestly perhaps most importantly, think about developer onboarding. Usually, tribal knowledge lives entirely inside the heads of your senior developers. With this framework, new team members instantly inherit this accumulated wisdom. A new hire totally bypasses the painful learning curve that originally produced those rules, because the AI agent they're paired with already knows not to make those historical mistakes.
Now, I know what every senior engineer listening is thinking. What happens when these rules inevitably clash? Because this organizational memory just lives in your standard codebase, governance doesn't need some clunky proprietary UI. Any contradictory rules are caught and resolved factually, just like a regular pull request. During the deployment, a general rule to always dispose of disposable types naturally clashed with a specific rule to never dispose of HTTP client factories. It was caught in code review, discussed by the team as a factual framework question, and resolved simply by updating the Markdown rule with a scope qualifier. Governance is beautifully built right into the tools your developers already use every single day.
So the absolute best part is that this framework is model agnostic, tool agnostic, and you can literally deploy it today using infrastructure you already have in place. It's time to stop fixing the same AI mistakes day after day. Which leaves us with a pretty inspiring question for your own engineering teams. How will you apply this closed-loop memory to your AI workflows to turn your reviewers into architects?